Okay, so I'll just share our screen then. Put up the slides. So welcome everyone. My name is Vishan, but you can call me V. Gabe.
Oh, and I'm Gabe, and the two of us, well, along with a couple of our other friends, run a nonprofit called Caribbeans for Climate. So we're thankful for the folks at Optics for having us to talk a little bit about the physics of climate, and we want to do this from a theory concepts basis, and then put it into practice with a Python tutorial. So we'll be going through that today.
Yep. So anything you see today, I mean, the goal of today is to really inspire you to include climate related stuff in your physics lessons. You'll quickly learn that climate science is physics essentially at the end of the day. The APS actually has a group that's dedicated to climate science. So we hope to inspire you to include some climate science in your coursework. And then also, if you have any students that are interested in getting into this field, you can pass them over to us and we can give them some advice. So, welcome everybody.
Welcome.
Okay, Gabe.
So we'll talk a little bit quickly about who we are, just to introduce ourselves to the group. And like V said, we'll talk about how climate science is, in our opinion, it's a really good way to incorporate a lot of different corners of physics into one consolidated form of field of study. But even climate science is, so broad. So we'll talk about how broad it is through some basics, introduce some concepts that we think would be helpful for students who might not have had an intro to earth science or a strong one in middle and high school to get some hands-on experience with some concepts, do it in a way that's relatable to concepts that they already know, and then put these concepts into practice using a Jupyter Notebook, which uses Python. So, like we were talking about before the recording started, Python is, you know, I think like Joe said really well, it's like the new calculator. It's super useful, it's accessible, and it's really powerful. So we'll put some of the concepts into practice with that. So a little bit about us and V, fill in the gaps wherever I miss. So V and I, we're representing Caribbeans for Climate. So we're a nonprofit community organization, and a few of us got together a couple years ago, and it's V is a climate scientist with Trinidadian roots. I'm a climate scientist with Cuban roots. Our friend Jordan Jones and Shayla Caceres, who weren't able to join us today, they're also from the Caribbean, and we all work in climate science, but we realize that there's a lack of people who, either look like us, speak the languages that we do back home, or serve communities that are being affected by climate change. And we wanted to get together, bring together this group of, knowledgeable and social scientists and bring in folks who are interested in the climate conversation, whether or not you're from the Caribbean or whether or not you're in climate science. If you're interested in it and you want to learn more about it, we're really trying to make this community inclusive and active. So, what you're seeing on the left and the right comes from AGU. So the American Geophysical Union is one of the main geoscience conferences in the US. And we had our first poster session, which you're seeing here on the right, that got great attendance, had a lot of exposure for early career scientists and students. On the left was our reception, which, I thought was just a great time. It's a good time to have a vibe with our friends after the conference is over. And really, we're just trying to bring community together, empower students and early career scientists, and bring attention to a region that we feel doesn't get enough.
Yeah, so I would add probably my biggest motivation with this it was to just have a good time and party with Caribbean people because we know that we're the funnest people to be around. So that's been really awesome. Also, try to promote the work of Caribbean scientists. So we have a monthly seminar series. We also do a graduate application workshop last year that we did with University of Puerto Rico Mayagüez. We do networking activities. So we are in the same boat as you all. We like to create community and then bring the light, bring the stage to our people so they can know what we're doing because unfortunately the people that have contributed the least to climate change are the most affected and it's about time that we had our voice empowered. All right. So, without further ado, we'll continue to introduce ourselves. So that was our organization. I'll introduce myself first. My name is technically Dr. Vishan Narayan Singh, but you could call me V. No formalities necessary. I was born in New York, but my parents moved here from Trinidad in the 80s. And I grew up my whole life in New York, half my life growing up in New York City, and then half my life growing up in like the farmlands of New York. It's pretty crazy dichotomy there. And then I'm actually a physicist, born and bred. So I did my undergraduate degree at CUNY City College. I did a bachelor's in physics, and my thesis was on quantum dot solar cells. So you could see some device fabrication I did there. And I was also a really bad student at first. Actually, the first time I took physics, I failed it and I had to drop it. And then now I have a whole PhD in it. So I always like to show people this because it shows that you persevere, even though you get setbacks, you still can reach whatever your dreams are. Eventually, I got my stuff together. I got into a physics PhD program. I wanted to do astrophysics because growing up, I was always learning about black holes, neutron stars, and I was like, this is what I want to do. But I couldn't find a advisor that would let me do research in their lab. So one of my professors approached me about this opportunity with NOAA, and I had no idea what NOAA was, but I knew that they would pay me and I would learn some coding. So I figured I'd just do this because I can just get a job at Google after because I'll know how to code. So, and become rich. But then I fell in love with climate science research, and NOAA was a huge, huge um, s- um, enabler for me to become who I am today. So I'm very thankful they funded my PhD, and that's also where I met Gabe. So I ended up doing my PhD on climate science, even though it was in physics, and I did climate modeling of persistent anticyclones, so stuff related to heat waves. After I graduated, I actually got a faculty offer to work at a liberal arts college, but then I turned it down to be a deputy director of a nonprofit organization. So I've done a lot of youth development work, and Gabe has been a great part of that as well. So I was working for the Harlem Gallery of Science, and then after a few months, I transferred to Princeton, where I worked as a postdoctoral researcher, and they have a cooperative institute with the NOAA lab there, Geophysical Fluid Dynamics Laboratory. And then eventually, um, yeah, I became a permanent scientist at the lab, and now I'm, I guess, living the dream. And right now, mainly primarily work in the climate modeling space, which we'll talk a little bit more about later. But and the other side of things, I'm very passionate about public service, so hence why one of the reasons we wanted to start Caribbeans for Climate. So it's been a really great journey so far.
Thanks, V. So, yeah, like we mentioned earlier, so I'm Gabe. So, I was born and raised in Miami. Both my parents came over from Cuba in the was in the 60s and the 80s. So, but I mean, if you've ever been to Miami, you realize that you never really left Cuba. So, I started up. Um, oh, could you hit the next arrow, V?
Yeah.
So I originally wanted to, I was always really interested in meteorology because, Miami got hit with a couple of big hurricanes when I was growing up there, but I never really saw a career in climate science or meteorology, at least not one that was lucrative. And, the old adage where like your parents try to push you to either go into law, go into medicine, go into engineering. So I figured engineering checks most of the boxes I'm interested in. So I got my bachelor's degree in that. And thankfully that got me into a space where I was able to, work in industry for a couple years. So I got some good experience. I was able to make some money and save up and help my parents. But I think after a couple of years putting in long hours, I realized that's not what I wanted to spend 40, 50 years doing. So I went back to school and got my degree in mechanical engineering. But at the same time, like V mentioned earlier, this fellowship sponsored by NOAA kind of let me have one foot in the engineering camp, but one foot in the climate camp and explore what it would look like to have a career in that space. And like V said, he organized a lot of great community work at City College, and I got to meet him and participate in that through there. And that's how we got started. And since 2022, I've been trying to wrap up my PhD at Princeton in atmospheric and oceanic science. And it's been a great experience with a lot of interested and knowledgeable people. So yeah, we're happy to put that to use here.
Right. Okay. So enough about us. Let's talk about climate science now. So if you're not familiar, I hope you will realize by the end of this is that climate science is physics. Recently, a few years ago, you've seen the Nobel Prize in physics actually go to a person that was working in my lab, Suki Manabe. And at the end of the day, it's just a different set of equations than probably some people are used to, applied to very specific problems. So instead of having the Schrodinger's equation like our quantum mechanics people like, we instead have the Navier-Stokes equations, but not just the Navier-Stokes equations, but them on a rotating sphere. So you have conservation of momentum, like you learn in Physics 101, your conservation of energy, conservation of mass, your ideal gas law. And these are our bread and butter when it comes to studying climate science from at least the fluid dynamicist point of view, like me and Gabe. And just like any good physics equations, you can approximate them, you can simplify them, and you can get wave equations like the one we see here. And when you solve those equations, they actually explain things you see outside. So if you ever seen these kinds of clouds in the sky where they look like ripples, that's actually from gravity waves, not gravitational waves, but gravity waves. So just like we have waves in E&M and so on and so forth, we have waves in the atmosphere, waves in the ocean, and it all comes back to fluid dynamics. But it's not just fluid dynamics, there's a lot of optics that's involved in climate science. So there's these satellites that are out in space, many of them, and all of them are containing some optical instruments that are continuously scanning the atmosphere, the oceans, the biosphere to get a sense of what's going on. So things like infrared readings, UV readings, LiDAR, radar. There's a lot of sophisticated optical stuff that goes into climate science as well. And also a lot of thermodynamics and radiation. So Gabe will get into this a bit later, but we have to think about astrophysics as well because there's the sun. We're a planet rotating around the sun. We have to think about the orbit of the Earth, how we're gaining energy from the sun, how when that energy comes in, some of it is absorbed. That's optics again. Some of it is passed all the way down to the Earth. Some of it is absorbed by the surface and re-emitted. So there's a lot of rich physics that's involved. There's also materials that are involved. You can see these gases interact with the different energy spectra coming in from the sun. So again, there's a lot of physics involved. I hope I can convince you that. And one bread and butter thing that we use every day is climate models. And Gabe will talk a bit more about that. But even I say it's physics, but it's other sciences too, because we need biologists like Laura here, who are also writing physics as well. And we need chemists who think about how those chemical species interact in the atmosphere. We need volcanologists. We need people that study vegetation. So climate science has a space for everybody. But at the end of the day, we're solving some equations that try to describe reality.
So what we're going to try to do here through this set of slides is present um, kind of a building block series of concepts that we use every day. So I know for the folks on this call, these things might seem, really basic, it's stuff that you already know, but if we're planning on having these slides be used for, the student body, hopefully we've collated things that we find useful. So something that took me way too long to learn the difference between was latitude and longitude, and I think that's a good place to start up. So what we're showing here is two diagrams of the Earth. And on the left, latitude is the distance from the equator, right? So north or south, latitude's, further north. And then if we talk about longitude, this is how east or west you are. So you'll hear coordinates that, your X degrees north, Y degrees east, or Y degrees west. And these coordinates are really useful for climate science applications. So as an example that we included here, Obi, do you mind hitting the arrow? So, so New York, for example. So if we were to look at this globe and you follow, one of the lines, you can see more or less that it's above that 30-degree label. And it's hard to tell here relative to the longitude plot, but we're about 74 degrees west. And this, it's something that takes some practice to distinguish the two, but once you get it down, it's super useful. And, it just sounds cool to say that you're like X degrees north, Y degrees west. So it's really useful. So besides latitude and longitude, the other things that we found are useful primers for students getting into climate science are getting comfortable with metric units. So for students in physics, I'm sure they're already exposed to this, but I know, you know, in public school and learning my curriculum as an engineer, we're really used to English units. So this is just a quick reference table. So in the top, it's just describing the units that we typically use. So we either use degrees Celsius or Kelvin. We use meters, grams, pascals for pressure. And getting used to these prefixes for a sense of scale has also been really useful for us. So we'll be talking about, pressure, atmospheric pressure is up in like the hundreds of thousands of hectopascals. We'll be talking about weather systems that are on the orders of, thousands of kilometers. So these are just the building blocks for the quantities we'll be talking about. So, well, I guess, yeah, I'll let you take this one since you're sharing the screen. So while he's pulling this up, we wanted to use this website named VentureSky. So this gives real-time weather data and presents it in this really easy to use interface that we think is also just really fun to look at and play with. Things are moving, there's a lot of stimulus. So we think this has been something that a lot of students have liked in the past. So what we wanted to figure out here was, using this map, and this is a question for you guys. If we're looking at, let's say, Miami, right? Something we could ask students is, what's the temperature right now in Miami? Is it raining there? And then can you find the coordinates based on the latitude and longitude demo we just gave, right? So if we go back to Venture Sky, so we look for this temperature field and we can choose where we want to look at. And we usually look at 2 meters above ground, which is about 6 feet. So that's what most of us feel. And we see that it's about 85 degrees there. But if we move our cursor around to pretty much anywhere else, right? So it's 85 there. V, can you see what the temperature is like in Ponce? So we can
It
tell Joel what it's like outside his
is.
window.
Yeah.
Very hot.
It's got to be around 85. Let's see. So it looks like hopefully you're getting a little sea breeze there. So I think it's,
Yeah.
yeah, a little bit more out to the east, but it's like, yeah, 84, 85 degrees. So, yeah, so it's warm, but we think this is a really good tool to, just test the basics on how to use a weather map and then look at different fields, right? So if we want to know if it's raining in Miami right now, we can hit the precipitation tab. And then you see kind of like what you see on weather maps on the local news. You see these precipitation patterns, you see the frontal lines, all these things that people are used to, but now they can explore it on their own terms, right? You don't need to rely on a weatherman or on a weather app to tell you what's going on. You can figure these things out for yourself.
Yeah. So I'll just
So,
give you a little tidbit here. You see how this precipitation map has these comma-like structures? You guys see that?
Yeah.
This is signature of an extratropical cyclone. So if you ever look at a precipitation map, you see this like this low in the center and this comma around it. That's an extratropical cyclone. Not a tropical cyclone, that's different. But this is an extratropical cyclone. So that's a nice little data visualization. It's fun for students to play around with. I put the link in the chat. Can you guys click it and go to it? And then we want you all to go find any place in the world. Maybe it's someplace you want to visit. Maybe it's where your family is from. And tell us what the temperature is and whether it's raining or not. So I will go to where my parents are from. They're from this small fishing village in Trinidad, right around here. And it's not raining. And it's about 86 degrees.
it's probably like 100% humidity too. Oh no, it's dry for you guys.
Good. Anybody find the weather in a place they want to share?
Well, it's 77 degrees in Fahrenheit in Houston.
Houston. Not
No
bad.
participation.
Oh, very nice. Anybody else?
Chris in the chat said that it's cool and not raining in Vancouver, where her grandmother just turned 100 years old.
Oh, wow.
Congratulations.
Yeah, glad I finally took a break from raining in Vancouver for her birthday. I feel like she got lucky on that one.
Nice. So yeah, again, this is a really nice resource for students to look at if they want to visualize. Um, okay, so I guess we can move on for the next part. All right, Gabe. Yeah.
Yeah, so like you mentioned earlier about astrophysics, a point we really want to drive home is the importance of the sun for the climate system. And I don't think this gets talked about too much in weather reports, but really the sun is it's the heat engine that drives our climate system. So not only is it the radiative part that I'll talk about later on, but it's also, the astrophysics of how Earth as a celestial body moves around the sun, right? And also the properties of the Earth that lend to the seasonality that we experience, right? So we experience these seasons due to the tilt of the Earth, and we experience our day and night cycle due to the rotation of the Earth. So, when you think of the Earth, it's kind of hard to think about it wobbling about its axis, but that's really the key to everything that we feel. And if we want to take this and take a look at how it affects radiation, we see that the arrow V. So what we're looking at here is a plot of radiation into the Earth's atmosphere. And as you can see, the x-axis is the month of the year. The y-axis is latitude. So again, north, south. And you see some patterns here emerge, right? So you see, if you just take any line, let's say across the equator, you'll see that on average over the year, we have really high radiation compared to anywhere else in the world. And that makes sense. The equator is going to be seeing the most amount of sunlight over the course of a year, way more than a place like, let's say, New York, right, where V and I are close to right now. It's going to be seeing a lot less. It's going to be seeing a lot more sun in the summer. So right now we're getting to like these 12-hour days. It's going to be seeing a lot less in the winter where we have these, like 6 to 7 hour long days, right? So this we can attribute to how the Earth is aligned relative to the sun, and that really explains this change. And it really depends on where you are. So if you hit the next two arrows, so this can help explain why people think of Miami as a place that's a lot more tropical, a lot more hot than somewhere like New York. You're at a lower latitude, your weather patterns are different, your climatology, which we'll get to, is different, largely as a function of this annual net radiation. So, like I alluded to, if sunlight depends on the time of year, temperature is naturally going to follow. So, taking a look at this net radiation over the course of a year, what you can see here is a distribution throughout the globe, where at low latitudes around the equator, you have the largest values of net radiation, reaching about 150 watts per meter squared. But as you move out toward the poles, this actually becomes negative. But this also does change a lot over the course of the year. So we'll also show plots of Northern Hemisphere winter, which you can consider Southern Hemisphere summer, right? This pattern of strong net radiation moves south of the equator because of how the Earth is tilted, and that leads it to be more exposed to solar radiation, and it leaves us in the Northern Hemisphere a lot colder. Well, us except for maybe Joel, but you know, things are a lot different here. But for somebody like Laura up in Pennsylvania, it's going to be frigid. But now in the summer, things are going to change a lot. And we pretty much flipped this over the equator. And, if you look at this for a really long time, you'll see that it's not just east to west that things are the same. There's a lot of, variability. So you see off the coast of California, you see over the Sahara Desert and Saudi Arabia, you see these things that change. If you look really closely, if you look over the Andes Mountains in South America, you see this radiation kind of change also. So we'll be talking about other factors besides solar radiation that contributes to different climates, but this is really the building block. for what we feel. So something else that we want to make a distinction between is weather and climate. So all of us are used to hearing about weather. We turn on the news, check our phones for the weather app, and we see the conditions that are occurring right now. So what I'm showing here on the left when we made these slides is a plot of temperatures at 6 feet above ground, 2 meters, on Tuesday. So this was what, almost a week ago. And you see a lot of like heterogeneity in temperature, right? So over the Great Plains, it's really warm, but if you look out over the Rockies, it's significantly colder, and you have a strong change in temperatures east to west. And that's one of those fronts that V was referring to. But then you go down to Miami, it's really hot. You go up to New England, and it's a lot cooler. And it's like this really patchy, this really noisy temperature data, right? And if we look at rainfall or precipitation, because we see snow and rain, you see that it's not like this smooth pattern. It's raining over Tom's house in Houston. It's raining out over our houses in New England, but it's pretty dry in Vancouver, right? It's pretty dry in the South, but we know that the South gets a lot of rain. Vancouver gets a lot of rain. New England depends on the time of year. So this isn't indicative of what's happening on average. So that's where climate comes in. So climate is what you expect, but weather is what you get. And the climate is when we average these weather conditions out over a really long period of time and we see patterns emerge. So let's take a look at this temperature map from 2017. So here, what they did was they took all the temperatures throughout the year, they averaged it over time, and this looks like what people think of when they think of how hot it is in different parts of the US. The South is hot, right? Miami, Houston, Corpus Christi, these are all hot, humid places. The Southwest, so anywhere from, LA out to New Mexico, it's going to be hot and dry. But then you move forward and further north and you get what you expect, right? In the Midwest, it's cooler. In New England, it's cooler. And what's also really interesting about this is that, like I alluded to in the radiation plots, you start to see some patterns emerge that aren't a function of like latitude, right? So you see over Colorado, you have these really cold patches. You see this cold patch extending down into North Georgia, and that shows where the mountains are, right? So it's also temperature is a function of elevation. And on average, higher elevations are going to be cooler than lower elevations. So a lot to consider when you think of climatologies. Same thing on the right, the south is wet, right? Whether it's thunderstorms now that it's hot out again, we get hurricanes. It's just a humid place, right? But then you move out to the west of Texas, you move out over the west coast, and it's really dry except for the Pacific Northwest, where it's almost always raining. And that's also thanks to the Cascade Mountains. So climate lets us take a look at long-term weather patterns and understand if a place is hotter, drier, cooler, wetter, and we can also learn about how climate changes with time, and we'll be talking about that later through these slides. So, like I referenced before, climatology refers to the long-term behavior of the climate. So what I was showing before was plots from 1 year, but climate changes on a variety of time scales, right? We know that conditions change over the course of a year. That's what the seasons are. So things are hotter in the summer, colder in the winter. But climate also changes over multiple year periods. So people might have heard the term El Nino or La Nina, and that refers to these multi-year oscillations of the climate due to sea surface temperature patterns in the Pacific. So during La Nina years, you're going to get more hurricanes in the Atlantic. You're going to get precipitation patterns change. El Nino might bring more extreme winters to the American Southwest. We're still learning a lot about this, right? And then we see this both in temperature and in precipitation. So climatologically, lower latitudes, especially near the equator, are more moist. But like we saw in the radiation plots, there's a lot of variability, right? Like the Sahara is really dry, even though if we look at the same latitudes over the West Pacific, it's really moist, right? And why is that? We also start to see, if you look really closely on the west side of the continent, so like west of North America, west of South America, west of Africa, you see these like these dry patches, right? It doesn't rain that much in California, and it has to do with ocean currents. We're not going to get into that, but climatology is really important to understand the Earth's properties, but also understanding how the climate changes over time is really important to know what we're doing to it. And climatology is the basis for the study of climate change, which we'll refer to later in the slides. So how does Earth balance the solar radiation, right? The sun keeps hitting us, but we don't keep getting hotter and hotter and hotter. So there has to be some balance going on. So we have this figure from Dennis Hartman's Global Physical Climatology book, which we'll have a link to at the end of the presentation because we think this is a really good reference. And what we're showing here is all the different ways that radiation and heat moves through the system. So we get radiation generally talked about in climate science in two bands. So there's shortwave radiation, which is this radiation coming in from the sun. And we usually think about it as shortwave in, so solar radiation into the system, and shortwave out. So that's solar radiation reflected by clouds or reflected by high albedo surfaces like ice, right? Um, is it high albedo or low albedo? I was getting confused. But really reflective surfaces that bounce light back up. So if you hit the next arrow. So this shortwave radiation band explains a lot of what happens with the heat balance in the Earth's atmosphere, but there's a lot that we're not accounting for, right? So we get about 340 watts per meter squared on average in, and we get about 100 reflected out. But what about the other 240? So that's where we talk about long wave radiation. So that's all these arrows here on the right. And this is how energy moves around through either terrestrial emissions. So if you guys think about a Planck black body, so the hotter the surface is, the more long wave emission it emits, usually out to space. But also, long wave radiation bounces around in the atmosphere. So long wave emission gets trapped by clouds, gets trapped by greenhouse gases. It gets emitted by water vapor. So there's radiation in both bands that are really important to consider and can be attributed to a number of processes. So, like V was saying, there's so much complexity in the climate system that we can attribute a lot of different parts or subdisciplines in physics to. So, like you mentioned earlier, and this is maybe a plot that we've seen in more general physics classes, we can really think about thermal emission in the shortwave spectrum and the longwave spectrum. So we know shortwave well, we see the sun and we see colors, but longwave is something we don't think about too much. And it's important to understand the distinction between the two and how they're affected, especially when it comes to the greenhouse effect. So I mentioned climate change and I mentioned how radiation is distributed through the atmosphere. So before we get into the radiative component of it, just a question that we have found to be useful with students we've spoken to is what happens inside a car on a sunny day, right? And I think anybody here can answer it, which is, sun comes in through the car's windows, and if you sit in the car for just a few minutes, even if it's cold outside, it's going to get really hot on the inside, right? So solar radiation can come in, but cars really aren't that reflected, so not a lot of shortwave radiation gets reflected out, and this heat gets trapped because the materials inside are heating up. As they heat up, they emit more, and this heat really gets trapped inside. It has nowhere to go. And we think that's a good analogy for the greenhouse effect. Also, we use the car because, who's ever really been in a greenhouse? It's not that common anymore. But this is a similar mechanism to what we're seeing in our atmosphere. So earlier I showed this plot where we talk about greenhouse gases and atmospheric components go ahead and trap and emit long wave radiation. So on top of water vapor and clouds, we have these other components in the atmosphere like carbon dioxide, methane, so on, that human activity contributes to, and they serve to trap this long wave radiation. So this is the part of the atmosphere that we're focusing on that human activity directly modifies. So if we go to the next arrow, so these gases trap radiation, they emit their own long wave, and in turn, they cause the surface to heat up. But like we talked about, when a black body heats up more, it emits more. So, and also water vapor is a really strong trapper and emitter of long wave radiation, and the atmosphere can hold more water vapor as it heats up. So more greenhouse gases, you trap more radiation, causes the surface to heat up, and it's a positive feedback loop. So when people talk about the greenhouse effect, it's this story, and we're directly affecting the composition of the atmosphere. So we want to understand how the climate system changes And we know how complicated it is. V showed really good diagrams earlier about how multifaceted the climate system is. We talk about human contributions to the climate, but it's really hard to do this science without using some computational help, right? As everybody in this group knows, there are a lot of equations that we can use to explain the world around us, but in the climate system domain, at least, we can't do these calculations for every point in the atmosphere, the ocean, the land. And we have a lot of observational equipment to tell us what the weather's like in a number of different places. This is an example of temperature stations around the US. And in the US, we're really fortunate to have this really spread out and developed infrastructure that's, among the best in the world, but not everywhere in the world is like this. And even here, you know, who knows what's going on in north central Colorado away from the highway? No one really knows, right? Or what about over Area 51? We're not really sure. So there are a lot of gaps in our observational network. So using computers to implement these equations on a domain that spans our whole climate system can help fill in these gaps. But that leads us to talking about three different types of models that we're going to talk about in our Python tutorial. So we have weather models, climate models, and reanalysis. So weather models are what we use to generate our predictions for 3, 5, 7 days out that you see on the news. So what you're seeing here is a figure from our friend Luis's paper about heat waves over New York. And what you see here is temperature data shown at really high resolution over Long Island and Manhattan. And this is very localized, very high resolution, and very high frequency in time. But we're limited to how we can do this over a large domain due to computational expense. Now, if you look at climate models, here we can look at a really large spatial domain and integrate this over a long time. But we're doing this over a large domain, so we have to make our grids a lot coarser, and we can get the level of fine detail that we can with weather models. Now, earlier I mentioned the gaps in our observational network. It would be nice to know what weather conditions were like everywhere, even though we don't have the infrastructure to know that. So what we use is a blend of climate models and observations, and we call that reanalysis. Basically, what that is we have all these different points of observations that we know is real data. And given the equations that we have in climate science, we can use those observations as constraints for our climate models and get basically our best approximation to what weather conditions were like anywhere in the globe. So it's not fake because it's constrained by observations, but it's physics informed observational data. So it's kind of like a halfway between models and observations. So we'll be using some of this reanalysis data for our data processing in our tutorial a little bit later on. So let's talk a little bit about climate modeling to get us into the spirit of the tutorial. So in climate modeling, we break down the Earth and the atmosphere into chunks, right? Anybody who has a computational background knows that discretizing a domain is a good way to start applying these equations to it. So what we do is we apply all the equations we've shown throughout the slides onto each chunk. And here we can solve for things that we care about at each point, right? So temperature, humidity, pressure, is it raining or not? Get all these radiation fluxes, and that informs us about what the climate state looks like. Now, if we go to the next arrow, so here at each chunk, if we just take one of these and zoom in, we have a ton of processes that we have to resolve at each point. So if you were to look at some of the climate models that V and I work with, here you have hundreds of thousands of lines of code, each of which resolves a different process and tries to get it ready for the next time step. So we can generate these model integrations that tell us what the climate system is doing over long periods of time and whether or not you're working on the ocean, on land, on atmosphere, on ice. Everything is attempted to be included in these climate models. And when you marry these two, this produces a pretty realistic representation of what's going on with Earth. So what I'm showing here is an output from the MPAS climate model that the folks in Boulder do. So the National Center for Atmospheric Research, they generate this really cool climate model, which is really useful for representing Earth-like processes. And if I were to take this grid off, it's really difficult to tell if this is a satellite image or if this is computer generated. So this goes to show that climate models aren't perfect, but there's been countless years of work that's gone into these to help us understand our climate system better and predict how it's going to change with time. So, as climate scientists, we can't say that we can predict the future, right? If not, we'd be a lot wealthier. But what we can do is that we can use the data that we have on hand to understand the certainty range of future scenarios, right? So something you might have heard is the acronym SSP, or the Shared Socioeconomic Pathway. So the Intergovernmental Panel for Climate Change, or the IPCC, they release these IPCC reports that inform the public on the state of the climate, and they also provide projections that climate scientists generate for how the climate will change with time. So when we talk about SSPs, there are a few different ones that calibrate for different potential scenarios, right? So let's say every government in the world decides to take drastic action on climate change and they employ climate mitigation actions, then that's a lower SSP number, right? So there's more action to stop climate change, effects are going to slow down. If governments take less action to stop climate change or accelerate it, so burning more fossil fuels, not cutting down on emissions, not cutting down on waste, that leads to this higher number, and that's this 5 to 8.5. And what these scenarios do is that they generate these potential futures, so we understand how our actions today have an impact for future conditions. So just to show a couple of examples from a report that we'll link to later, here's projections for each SSP. So the light blue one is SSP1. So this is the most extreme climate action. And the dark red is SSP 5 to 8.5, and this is little to no climate action. And this is showing the progression of sea ice coverage in the summer over time. And as you can expect, if we start to take action to mitigate the effects of climate change, we can preserve sea ice, even though it's still supposed to drop from current conditions. But if we continue on our path, we expect sea ice to fully melt in the summer by the end of the century. And this is a multifaceted report. So we can talk about sea levels, and like you'd expect, sea levels don't increase as quickly, although they still increase substantially with more climate action, but they increase drastically more if we don't take any. And if you take a look at 2 meter air temperatures, same deal. We don't take the climate action, temperatures get hotter on average. If we take more climate actions, well, we can stop the warming. It's still going to get warmer, but at least at a slower rate, and we can adapt to those changes. So we're going to be talking about some of these SSPs in our tutorial, and these are generated using the tools that we've talked about previously. So we wanted to share some resources that we find useful to learn more about weather, climate, and climate change. And these are targeted for really students of any age, but these I think are especially useful for 2 year college students to get an introduction to what this looks like, as well as a good springboard to future literature if they want to read more about it. So we talked about the IPCC report. This one has a lot of press coverage. It's used by government organizations and NGOs worldwide. And they have a hierarchy of different reports. So some are in more plain English and easy to read, and these going to show some of them, and they have what I think are great graphics. They're really good at scientific communication. But if you're really into it or you're just bored on a weekend, you can open up the really big report, and scientists put years and years of work into each version of the report to document what their best guesses are for the future, informed by the physics that we all know and love. So we also share some resources to, this textbook that I referenced earlier by Hartman. So Global Physical Climatology provides a really holistic and accessible approach to climate science and the concepts behind it. And like V mentioned earlier, there's a lot of different subdisciplines of physics that go into climate science. And I think this book does a good job building that physical intuition from the general physics that we all learn in, our physics 1 and 2, and then expand that to some of the concepts that we've been talking about today, and just a million others that I can't get into. This also has really nice figures, which I know students like. We've shown some figures from Climate Reanalyzer, and this is an open source tool that's available daily thanks to the University of Maine, and we think it's super useful. And lastly, oh, this is a good one. Oh wait, do you mind going back to that one, V? I think that was a good Yeah, so they have these plots showing like sea surface temperatures from observations. They show anomalies relative to climatology, which we haven't spoken about. And this shows us how current conditions line up with previous years, right? So that dark red line is our current conditions, and all the gray lines are conditions from the years past. This orange one shows the record, and things are pretty close to, record warmth. So this gives good context for what the current state of affairs is in our climate. And lastly, Earth Null School, like Venture Sky earlier, this provides a really cool map that you can play around with. If you go to the bottom left menu V, you can change the field. So, if we want to talk about, ocean conditions, we can talk about currents. Uh, this is a really good way to show students what's going on from a different number of perspectives. So, if you ever have a lecture and you want to show something that's really interactive, we've had really good experiences with this website. And all of these, except for the textbook, I've been free to use. So we really appreciate that. All right, Jay, I've been talking for too long. You can take over.
All right, so we're gonna start getting into the tutorial now. But how are you all doing? Are you still with us? You falling asleep or? Okay, good. All right, so just on the scientific piece, does anybody have any quick questions before we get into the tutorial? Okay, cool, 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 cool. All right, so now let's talk about the tutorial. So, like we were saying, climate science is physics. So, some of the physics concepts that you'll encounter today in the tutorial are unit conversions, numerical analysis, radiation and optics, astrophysics, and some thermodynamics. But there's also going to be some data science concepts that we're going to cover. We're going to cover Python and Python packages. We're going to cover data storage and matrices. We're going to cover data indexing, averaging, and then plotting and data visualization. And then in terms of the climate science jargon, we're going to go over some things like latitude and longitude, climatology, what a temperature gradient is, Earth's energy budget, and the different climate projections, SSP scenarios. Um, and then, of course, like any good teacher, we have some learning objectives for this tutorial. So we want you all to learn how the Earth's temperature is distributed on its surface seasonally. We want you to learn about climate data sets and how to process, analyze them using Python. We want you to calculate and visualize the temperature climatology for current climates. We also want to do the same thing for future climate projections. And then calculate and visualize temperature in the future climate projections and how that changes relative to the current climate. Okay, so now we're going to get into the tutorial. So I'm going to put this link in the chat. You need a Google account in order to access this. So I think Chris sent a reminder. And here's the link. So if you click on it, it'll open up something called Google Colab. Now let me know if anyone has access issues. And you should see something that looks like this. If you have any issues, just unmute yourself, let us know, and we will help you. Give me a thumbs up once you're on, once you see what I see. Joe, Chris, you all able to access? Okay, Laura's good. Joel? Oh, you're muted, Joel. I don't know if you're talking. Joel, did you get it?
No, not yet. I'm getting like a notebook loading error.
Notebook loading error? If you're having trouble, Joel, you can maybe share your screen and we can see if we can help you if you want. Very good. All right, so we all got it open. Just before I forget, I just want to drop some other information before we fully begin. Just want to really remind you that climate science is physics. We're going to go through this data science piece, but if you're interested in joining Caribbeans for Climate, you can go to our website. There's a sign up button on there. It says join our community. And then you could also email us if you have any questions. We are fully available if you want to have us do a tutorial in your class. You can Zoom us in. Um, and then we also have a film series that we have made that we made the first episode and we are working on making more, but it's called Ripping the Gates Down, the Real Stories of Scientists. So in the recently we started doing film screenings at different minority serving institutions. So we're also available to show our film and do film panel discussions. And then of course, as any nonprofit, we're always looking for money. So if you feel so inclined, here's some links to donate to us. All donations are tax deductible since we are a nonprofit organization through the IRS. So I'll just put that up here and then we can share again later. But for now,
Yeah.
yep, go
Oh,
ahead.
sorry, be real quick. Just to echo something that Veet mentioned at the start of the presentation. If you do have students that are interested in learning more about climate science, please feel free to put them in touch with us. We're always happy to, connect students with more resources and help them build a network. So, yeah, just let us know.
Yep. Okay, cool. So with that being said, let's go into this tutorial. So everybody sees this front. So I guess I'll share my screen and do it with you, but you should also be working on the tutorial yourself. That way you can change it however you want. And this is the first cell. So you'll notice that it's separated into different sections. These sections are called cells. This is a Jupyter notebook. And we first have to install all the packages that we need to analyze our data. All right, so you can go and click the play button. It's going to give you a warning, but that's all right. We're not trying to give you a virus. It's all on your Google Drive, by the way. So if you press that play button, what it's going to do is initialize all the packages that you need to install the data. So here it's going, and it'll let you know when you're done. If anybody has any issues, you just unmute yourself and let us know. We'll help you right on the spot. Takes a few minutes. So, yeah, and what's nice about Python is that it's completely free and you can use it to do a lot of different things. And people have these open source packages that you can use to do whatever you need it to do. So each one of these packages does something different. Cartopy, for example, that's what we use to plot maps. NumPy is what we use a lot. NumPy is what we use a lot for our mathematical operations. So each one of these packages does something different. So as you can see, everything is installed. It gives you a bunch of crazy looking words, but this just means that everything is installed and ready. Okay, everybody with me? You got that first cell done? I see nodding. Okay. Now let's go to the coding part. So here in this code, what we're doing is importing all those packages that we just installed. So we're basically activating them. And we're going to download the first data set that we're going to use. So we put the data set on Google Drive. And what this is the 2-meter temperature. So it's the temperature near the surface from reanalysis from the years 2015 to 2019. So what this is going to do is going to download the data from this link, and then we're going to load it in. That's what this open data set thing does. You can go ahead and you press play, and it will do all that. So this is a very simplified tutorial. We give you a lot of the starter code, but for your own adaptation purposes for your class, maybe you give them a little bit less. Up to you. So as you can see, the data downloaded, all of it's being saved to your drive right now. It's a pretty small file. It's only 94 megabytes. So now that we've downloaded the data, we loaded it in. Now let's get a sense of what the data actually looks like. So here, I'm just going to call the data. I named it ERA-DS, and that means ERA dataset. And now let's just get a look of what's in the dataset. So I'm just going to call it. Press play, and you can see that the data is formatted in a certain way. So first of all, the data has 1,826 time steps, which makes sense because we're looking at 2015 to 2019. So it's the temperature everywhere on the Earth every day in that time period. And that there's 90 latitudes that we're dealing with and 144 longitudes. So these are the dimensions of the data. It's three-dimensional. It's one dimension of time and then latitude and longitude. So it's three-dimensional. So you can think of the data kind of like a cube, right? Where each slice of the cube represents a map, and then each of those slices is a different time period, a different day, basically. And then, so you have the coordinates, the dimensions, and then the data variables. So in this data set, the variable is something called TAS max. That means temperature, max surface temperature for the day. So we're going to keep this in mind as we reference the data and then plot it. Okay, so first we got to load in the temperature data. So to load in the temperature data, and to analyze the data, by the way, we're using something called Xarray. Xarray is a nice package that is used to reading in climate data. And the data type the file type that we're using is something called a netcdf file. So Xarray is really good at working with netcdf files. So first, we're going to load in. Yeah.
I'm sorry to interrupt.
Yeah.
Is there some way to make the font larger? It's
Oh, yeah,
a little
sorry.
hard to see.
Sorry.
No worries.
Is that
Thank
better?
you.
Is that better?
Absolutely. Thank you.
Okay, very good. Sorry about that. So we are going to first load in that temperature data. We loaded in the data set. Now let's pull the temperature from it. So to do that, we type in ERA temp. We just name a variable, and then we say ERA-DS dot TAS max. That's going to pull the temperature for us, the temperature variable. And then we're going to convert it into Fahrenheit because I'm used to thinking about Fahrenheit. So it makes it a little bit easier for us. And we're also going to load in the latitude, the longitude, and the time dimension. So all of these are just loading in the temperature data, converting it to Fahrenheit, and then loading in the dimensions as well. Go ahead and run that one. Now, these starter codes are just to get you started, but soon we're going to have some exercises where you're going to change it yourself. Next, we want to get a sense of what the data actually looks like. So we're going to select the data just for January 1st, 2015. So to do that, we take our data variable that we made, ERA temp, and we're going to say with the temperature that we want, we're going to create a new variable, and we're going to select the time that we want it from. So this is going to be January 1st, 2015. All right. Just a quick question for you. If I wanted to get the data, if I wanted to select the temperature for April 1st, 2015, what would I change here? Does anybody have an idea?
The time, the 04.
Yep, exactly. So I would change this 01 to 04. Okay, so I'm not going to get to the nitty-gritty details, but this is basically setting up the colors. So we want our minimum temperature to be 30 on the map. We want the max to be 110. We want 15 different colors on there. So this is all just to initialize the figure that we're plotting. And then if you go down and you press play, you will see that it will generate our temperature map. And this is similar to what Gabe was showing earlier, but different colors. But just to check some of our concepts, where is it coldest on the Earth right now in this picture? What colors do you see in the coldest areas?
Purple.
Purples? Yep. And where are those coldest areas located?
Above or below 60 degrees latitude.
Yeah, so just as we were talking about earlier, as you go to higher latitudes, you get colder. And then what kind of colors do you see towards the middle of the map?
Light blue, so I mean
Yeah,
light green.
yeah, you get some greens in there, and that means warmer colors. So near the equator, it's warmer, right? Okay. So also, I have a question for you. Which is warmer, the northern hemisphere or the southern hemisphere in this plot?
Southern.
Why is that?
Larger regions of warmer temperatures
Okay. Why are there regions of warmer temperatures there in the southern hemisphere for the state?
because it's January the 1st.
Right, Joel, were you about to say something?
Yeah, I think yeah, you guys mentioned it. The tilting
Yeah,
when it's winter in the north, it's like summer. They are getting more light in the south.
exactly,
So it's
exactly.
like summer in the south and winter in the north.
That's very good, very good. Excellent. So we just answered some of these concept questions. Now it's your turn to kind of do it on your own. So what I want you to do is plot the temperature for January 3rd, 2015. So what you can do is just copy this whole code, copy it, and then copy it, and then paste it into this cell with the exercise, and then modify it so you can get a plot for January 3rd. And let me know when you get that. See four. Exercise four, it says plot the temperature for your birthday or someone you love or someone you admire's birthday in 2017. So do exercise four. The other ones you can do on your own. I'm gonna skip around a bit because they're kind of pressed for time. But yeah, you can plot the temperature for July and you can see how that is different from January 1st, especially with regards to the different seasons. As Joel was letting us know that when Northern Hemisphere is in summer, Southern Hemisphere is in winter, and vice versa. So now we're going to calculate the climatology and then plot it. So to calculate the climatology, what's nice about Xarray is that you just put in some simple command and it'll do it for you. So to calculate the climatology, we just take an average. We go to ERA temp, the variable that we made, and then we just type in dot mean, and then we have to say what dimension that we're averaging over. We're averaging over the time dimension. Well, this is crazy. This got the AI interface too on Colab now, so it helps you. But this will average it over the time dimension, and you'll just get one map of the climatology. So you can go ahead and run this one. And what this will show you is the average temperature everywhere in the world from 2015 to 2019. So now let's just talk about this a little bit. So this is now the average temperature for that 5-year time period. How does this compare to the temperature maps that you plotted when you were just plotting days? How does it look?
Different.
It looks different. How?
Well, the colder temperatures are definitely on average, are in the southern hemisphere.
Oh yeah, that's true. Antarctica. That's true. What about the overall how the colors look, how they're distributed?
They're cooler.
They're cooler.
Eh,
Any other things that you notice? Family? What about like the noisiness? How does the noisiness compare when you're just plotted a single day versus now the climatology or the smoothness of the plot?
I was gonna say it seems less like there are fewer fluctuations. It's a smoother, more even.
Exactly, exactly. The map is now more nice and organized. You see, we have some nice smoothness to the colors. Um, Rather than when we go and we look at just any given day, it's a lot more uh rigid and noisy and fluctuations going on. So climatology, like what we were showing here, this is the weather for that particular day. But when we look at the climatology, this is the climate for everywhere on Earth during that 5-year time period. So it tells you, you get a better sense of where it's the coldest, where it's the hottest, and so on and so forth. Okay. Now let's look at the climatological values for some specific places. So we have our map of the climatology. Now let's look at certain particular cities or areas and get a sense of what the climatology is like there. So I located one area, our first location, that's Paris. And to get the climatological value for Paris, what you have to do is take that climatology variable, and then you have to select the latitude and longitude that you want. So you're going to put in the latitude value, the longitude value, and it'll spit out your Paris annual temperature. And then we did the same with New York, and then we did the same with Trinidad as well. So if I go ahead and play this, it's going to tell me the annual temperature in Paris. It's going to tell me the annual temperature in New York City, and then the annual average temperature in Trinidad. So Paris and New York City are pretty much the same because they're at similar latitudes, but Trinidad is obviously way higher because it's in the Caribbean where it's a lot hotter. And then I want you to take this same code, copy and paste it into the cell underneath, and I want you to find the annual temperature for a location of your choosing. So you're going to have to look up the latitude and longitude for wherever you want to do it and show us and tell us what the temperature there is. Interesting. Okay, very good. So you see that certain places have similar temperatures. There's some prompts here, but you can we can go over that another time. So now we plotted something called the annual climatology. So that's the climatology for every day of the year. Now we're just going to do the climatology for Northern Hemisphere summer. We typically refer to that as JJA, which stands for June, July, August. So as climate scientists, if you ever want to fit in, you say, instead of summer, you say JJA. So I can't wait for JJA vacation. So here is the code that you use for JJA. You'll notice that before we take the mean, we have to put in some other commands because we just want to select the months June, July, and August. So if we go and run this, it's going to give us the JJA climatology. Now let me ask you a question. Here is how we take the climatology for JJA for summer. Let's say I wanted to do it for winter. In winter, we call that DJF, which is December, January, February. How would I change my line of code here to do winter? Does anybody know?
The numbers of the month.
So what would I change?
12, 1, 2.
Yep, so instead of 6, 7, 8 for JJA, I'll have DJF 12, 1, and 2. So we can go ahead and plot the climatology for JJA. We'll calculate it and then it'll plot it. And you'll see now, Tom would love this, is that the map looks very different from what we were looking at for the annual climatology. And now the northern hemisphere is much warmer than what we saw before, and the southern hemisphere is much colder. Make sense? So there's an exercise here where you can do the same for DJF, but we'll skip the exercise. You can do that on your own, or maybe your students can do it. And now let's just look at some really quickly. Let's look at some of these climate projection data. So if you scroll down now, here is some climate projection data. Now, this data comes from NOAA. It comes from a lab called Geophysical Fluid Dynamics Laboratory in Princeton. It's a really nice lab. It actually is the place that invented climate modeling. And they've won the Nobel Prize in Physics for their climate modeling work. They made a prediction about climate modeling or climate warming about, was it 40 or 50 years ago, about how much the Earth would warm up by, and it's been pretty much spot on. So that's why they won the Nobel Prize. So this lab, it has all these different climate models and they do climate model projections. So they took each one of these SSP scenarios that Gabe was alluding to earlier, and it created simulations of what the climate will be like in the future. So here, what we're going to do is we're going to download the data for SSP5. SSP5, sometimes people call it business as usual. That's like if we don't do anything to mitigate climate change. And let's just look at the years 2095 to 2099. So you can go ahead and it'll download the data and then it'll also load it in for you and convert it into Fahrenheit. So it's downloading, it loaded it in. And there's an exercise here for you to calculate the climatology on your own, but you can skip that. And then we can go down to this cell after it. And this will calculate the climatology in the SSP5 data. And then it'll plot it for us. So this is what the climatology looks like in the SSP5 data. And then if you scroll up, I'm not going to do that, but if you scroll up, you will see that it looks very different from 2015 to 2019. I guess if you guys want to scroll back and forth, can you tell us how it looks different from 2015 to 2019?
Well, one noticeable difference is that the warmer temperatures are broader.
Yeah, so it's much
Mhm.
warmer, right? Exactly. Very good. So now let's get a sense of how this change in warmth looks like throughout the globe. So here I'm just gonna run the when we extracted certain regions, certain cities, I'm gonna run that code and we can see what the temperature is like now. So now Paris, for example, has gone up to almost 66 degrees. New York City is now about 69 degrees. Before it was like what, like 58 or something. And then Trinidad has gone up almost 7 degrees to be around 88 degrees Fahrenheit. So by the end of the 21st century, if we're going on the path that we're on now, which is not doing anything about climate change pretty much, we're well on our way to be about, 7 degrees warmer in some places. I mean, some places are doing stuff about climate change, but the major contributor, the US, is not doing much at the moment. Okay, so then really quickly, we can get a sense of how much the temperature changes everywhere. So this code right here just takes the difference between the two climatologies. So I ran that, it gives me the difference. And then this next code is going to plot that difference. So we can see when we plot that difference that it doesn't warm up by the same amount everywhere. It's kind of different depending on where you go. So now we're looking at the plots in the different scenarios. So the temperature by the end of the 21st century minus the temperature from 2015 to 2019. What do you see? Where does it warm up the most and where does it warm up the least?
Most in the Arctic and regions.
Oh, that's a very good point. So this is something called Arctic amplification. So when the Earth warms, it warms up the most near the Arctic region. Where does it warm up the least?
The Southern Oceans.
The southern oceans and just the ocean in general, right?
Mhm.
So does anyone know why the ocean warms up less than the land?
Does it have to do with the heat capacity of water?
Yes, exactly. So the water has a lot of heat capacity. It's very deep as well. So it takes a lot more energy to change the temperature of the water than it is to do the land. So again, climate science is physics. Okay, and then when we look at other places in the world, if we look at the Amazon, for example, that's poised to get a lot warmer than other places with similar latitudes, which could be quite catastrophic because if we lose the Amazon rainforest, that'd be very bad because it's a huge carbon sink. So this is just one scenario, SSP5. There's some prompts that go along with that, and I'm just going to skip through these last cells pretty quickly. There's also a SSP2 scenario, so this is like a middle of the road scenario. You can download the data. You can load it in. Then you can plot the data as we did before. And then I'm just going to skip ahead. This is the difference. Yeah. So this is now going to show you in the SSP2 scenario how much it changes relative to the 2015 to 2019. So how does the SSP2 compare to the SSP5?
Yeah, not a lot of change.
Yeah,
Like,
so it's not, and this is just like with medium intervention. So before we were kind of look at an unabated business as usual type of scenario, but there's an intervention, and you can see that it does not warm up as much as the SSP5 scenario. So there's other scenarios. We just chose two to look at, but they can give you a real sense of how the climate might change in the future. Here we're just looking at temperature. You could also look at precipitation. You can look at sea surface temperature and effects on coral, things like that. But there's a lot you can do with it. And then underneath you'll find some other exploratory prompts that you can check out if you'd like. But with that being said, I think we spent enough time and we'll wrap up here. So thank you all for having us. This was really fun. And like we said, we're available if you want us to come do a tutorial in your class or anything else. If you want to talk to us to talk to students, we're here. And definitely feel free to join our community. It's open to anyone. You don't have to be from the Caribbean or of Caribbean descent. We're a family here at the end of the day. So again, thank you, and we'll take any questions.